Howdy, Calc BC. Welcome back. This week, short week, we just have the one day. We are transitioning to something called series convergence now. Uh, we talked last week about sequences and how sequences might converge. And so today the transition is to now the sum of that sequence, which is called a series. And we're going to use some sigma notation. So let's get that up here on the whiteboard. There we go. And with sigma notation, we've seen it before. We saw it when we did Riemann sums for integrals and stuff. We're summing, and we're going to say from 1 to infinity, because we're going to be doing infinite series today, of the terms a sub n, which means a1 plus a2 plus a3, and so on and so forth. So with these series that we're interested in, these infinite series, we're adding up an infinitely long string of numbers. Our concern is going to be, does this series converge to a finite value? Which may seem a little weird in some ways, we're adding up this infinitely long string of numbers. But at the same time, we've seen this before. We've seen with integration, how integrals can add up an infinitely large string of numbers to get a finite value for an area under a curve, for example, or an accumulated rate of change of whatever. So we're going to do it in a more discrete fashion this time. And so the idea is to take a look at an infinite series and see how do we show that it converges, and what do we even mean by it converges? Okay, and so let's start there with what do we even mean by convergence? I think you get it, that we mean it adds up to a single value that's not infinity. How do we show that though? We invoke something called the partial sums, and so the partial sums of a sequence. If I'm using that sequence above, partial sum number 1, S1, is A1. S2 is A1 plus A2. S3, you guessed it, A1 plus, didn't mean to do that. Come on, undo. There we go. Plus A2 plus A3, and so on and so forth until we get to the nth partial sum, which is S sub n, and that's obviously A1 plus A2 plus A3 plus a whole bunch of things up until we get to A sub n. And you're probably looking at that going, well, that's kind of making a sequence, isn't it? The first term of the sequence is S1, the second term of the sequence is S2, third term is S3, fourth is S4, and so on. And that's how we define convergence formally with our infinite series. We say, look, if you look at the sequence of partial sums, okay, then if that sequence converges to a value, then we can show that the series converges to that value. And so again, we're thinking back to last week, so we look at that sequence S sub n and we say, oh, okay, so is it monotonic, for example? Is it bounded above and below? Then we can prove that that sequence does in fact converge. And more importantly, if the sequence S sub n converges to something we just call capital S, then the series converges. Okay, and S is the sum. So there we go. If the sequence doesn't converge, well, then neither does the series. Okay, so if S sub n just keeps getting bigger and bigger and bigger, yeah, then the series isn't going to converge. So that's how we define it. And so we'll look at a couple of examples here real quick. These are pretty straightforward, I think. The first one here says, look, let's consider the series 1 over 2 to the nth power, and n goes from 1 to infinity, like so. Okay, so basically we have what, 1/2 plus 1/4 plus 1/8, so on and so forth, right? If we look at the partial sums then, right, S1 is 1/2. S2 is 1/2 plus 1/4, so 3/4. S3, well, 3/4 plus 1/8, right? So that's 7/8. And so are you starting to see a pattern emerge, right? We have 1, 3, 7 over, and then we have 2, 4, 8, right? So what is S sub n look like in this particular series? Well, then the numerator, you got it, it's 2 to the nth power minus 1, and the denominator is just 2 to the nth power. Okay, so now the question is, does that converge? Well, just like in the last thing, let's think about what is the limit as n approaches infinity, okay, of 2n minus 1 over 2 to the n. Okay. Well, if you're looking at that going, hey, that's an infinity over infinity, couldn't we use a L'Hopital's rule? You sure could. And what you would get, right, is the limit as n approaches infinity of natural log of 2 times 2 to the n over natural log of 2 times 2 to the n. Hey, that's 1. So the nth partial sum, right, 2 to the n minus 1 over 2 to the n, as n goes to infinity now, so the sequence converges, it converges to 1. So our series, you add up all those terms and it will converge, and it's going to converge to positive 1. If you have this sneaking suspicion like you've seen that series before, you have, and we'll talk about the geometric series here in just a minute. So yeah, there's lots of different kinds of series that we could look at. That's a geometric, and we'll talk about a geometric in a minute. There's something called a telescoping series, and this is probably a new one. Telescoping series, and a telescoping series is really cool because it's got this this awesome feature where the terms, when you map them out, the first term and the last term are the only ones that remain because all the middle ones cancel each other out. I'll show you what I mean. It's pretty cool. So let's see, this one is n equals 1 to infinity, and I've got 1 over n minus 1 over n plus 1. All right, so there's my series. Now let's just watch what happens when we put these terms together. So obviously the first term is 1 minus 1/2. Okay, that's our first term. Plus, now if n is 2, right, we get 1/2 minus 1/3. See what's happening? And then we get 1/3 minus 1/4, right? And so on until you get 1 over n. Well, you get the idea. Let's not jump there yet. So notice what's going to happen if I just redo the grouping symbols. You could see how all of these middle term, oops, that's an eraser, sorry. How all these middle terms, that's going to cancel out, that's going to cancel out, those would cancel out. So in the end, what ends up happening, right, is you get that, you get the first term plus the last term. And what happens to this as n goes to infinity, right? Well, you get 1. Okay, so the sequence of partial sums, right? S sub n would be 1 plus 1 over n plus 1, and you get 1. So again, our telescoping series converges. These are pretty handy. So I got to say, the telescoping series, they will always converge to the first term. The nth partial sum with the first term minus the last term, and so you get this nice convergence every single time with the telescoping series. So we're not going to see it a lot, but it's kind of a fun one when you get it. All right. Let's go back to the geometric, because that's the one you're going to see some more. So in a geometric series, now you probably remember this from some stuff we did earlier in your math career, but a geometric series for us is we start. You can start at 1, you can start at 0, it doesn't really matter. But you always have the first term times the common ratio to the nth power. Okay, so basically what it means is every single term in the series, you just, oops, sorry, that's supposed to be plus. You just multiply by the ratio again, like so. So we're, when we think back to the one I said, hey, look, it's a geometric. Notice each time, what am I doing? I'm just multiplying by a half, right? Take a half times a half, you get a fourth. Take a fourth times a half, you get an eighth. Eighth times a half, you get a 16th. So the geometrics are very, very handy to recognize. More importantly, an infinite geometric will converge. Okay, this will converge if the common ratio is between 0 and 1. And actually, the terms can alternate between positive and negative. It won't matter. So we can have the absolute value of the common ratio between 0 and 1. It will converge. Not only will it converge, but the sum of that geometric is simply a over 1 minus r. So the first term divided by 1 minus the common ratio. So geometrics are super handy. We are going to use these a fair bit here as we work our way through this whole unit here in chapter 8 on sequences and series. So take a look at your series, and if you suspect that it is a geometric, then check out and see if you have a common ratio. So here's my series that I've got here. N equals 0 to infinity, 3 over 2 to the nth power. Now, I'm going to rewrite this a little bit, but let's write out our terms. So the first one, 3 over 2 to the 0. Okay. The next one, 3 over 2 to the first. The next one, 3 over 2 squared. The next one is 3 over 2. You get the idea. Okay. In other words, a rewrite of this would say, oh, I know, it's 3 times 1/2 to the nth power. Okay, see how that's the same thing, but now it looks a lot more like our geometric, right? Now, common ratio in this one, okay, here's R. And notice it's less than 1. So as long as the common ratio is smaller than 1, then we know this will converge. So the series converges to take your first term, divide by 1 minus R. And sure enough, we get 6. So the geometric converges, and it converges to 6. All right, pretty cool. Now, that is a drastically different result than if I had written this series. Just to be clear. right? Because in that series, the first term is 1, right? And 1. The next is 3/2. What's the next term in the series? Well, that's 9/4, and so on and so forth. Notice though, now the common ratio is 3/2. That's greater than 1. This series is divergent. It doesn't approach a single value. It blows up, it goes to infinity. So that's another thing with geometrics, is we can see divergence pretty easily as long as the common ratio is greater than 1. I'm not going to go through theorem 8.7 with you. I just point you to page 571. You can see 8.7. Those are just some properties of infinite series. You know, the things I think you would expect. Like if there's a coefficient in there, you can take that out, put it up front of the summation. You can add the two series together. You can sum them separately. Those kinds of things. Nothing too earth-shattering there. What I want to finish up with are there's two theorems here, 8.8 and 8.9. 8.8 says this, and this is, so where are we? Theorem 8.8 says, if the series is convergent, then the limit as n goes to infinity for a sub n is 0. Okay. So if we know the series converges, then we can use that and say, well, then obviously the terms of the sequence a sub n must approach 0. Okay. You can't be adding on infinitely values that aren't approaching 0. Okay, so if it converges, then we know the limit of a sub n is 0. All right, and that's not a terribly earth-shattering theorem. I think we can all kind of get our head around that. The one that I want to make sure we hit, and this is one we're going to use a fair bit going forward, theorem 8.9. It's also called the nth term divergence test. And this one's a little bit different. We reverse that statement from above and we say, look, if the limit as n approaches infinity of a sub n is not 0, okay, then the series n equals 1 to infinity a sub n diverges. And I want to be really careful here, because these are conditional statements that are one direction only. Okay, if the terms of the sequence don't go to 0, then we know the series n to infinity of a sub n diverges. Okay, if we know the series converges, then we know the terms of the sequence go to 0. Okay, notice what none of this is saying. Okay, none of this is saying that if the sequence of terms approach 0, then the series converges. We're not saying that. Okay, in fact, you absolutely cannot say that. It's because it's not true. Okay, so really important that we understand what this does not mean. Okay, so let's take a look at an example, a couple of examples actually, where so I have my first example here. The series goes from 0 to infinity, and it's 2 to the nth power. Okay, so let's take a look here. What happens as n goes to infinity of 2 to the n? Right, that goes to infinity. So for series A here, what happens? Well, we know if this is not 0, okay, then this is divergent. The series diverges. here's a series for you. N equals 1 to infinity, n factorial over 2n factorial plus 1. Now, the limit as n approaches infinity of n factorial over 2n factorial plus 1 is a half, also not equal to 0. Okay? And therefore, our series diverges. Okay? And in both these cases, the reason is by the nth term test. Okay. Let's check out series letter C. Okay. It's 1 over n. Okay, so let's think. Okay, what happens to 1 over n as n goes to infinity? That's 0. That doesn't tell us anything about the convergence of our series. Okay. And that's what I wanted to make sure that we got. Okay, in this case, okay, just because the limit of the sequence, the terms of the sequence is 0, doesn't tell us anything about the convergence of this. The test in this case, the nth term test, sorry, is inconclusive. Okay. It does not tell us anything about the convergence of this one here in letter C. The convergence of 1 over n is actually, it doesn't converge. It's the series 1 over n is not a convergent series, it's divergent. So we have a problem that the nth term can't tell us whether that converges or not. So good news is, don't worry, later in this chapter, we will be getting some tools in our toolbox that will help us determine the convergence of 1 over n. But we, right now, for what we know in section 8.2, that series is not one we can determine the convergence or divergence of as it sits right here. Now, what could we do? Well, we could go back and we could start looking at the partial sums, right? Because we could figure out what the partial sums are doing. Okay, and then using the partial sums, we could then say, oh, okay, now I see how the partial sums, that sequence doesn't converge. Okay, and then you would know it was divergent. But in the case of the nth term divergence test, theorem 8.9, I wanted to show you that it's great for determining divergence, but it doesn't do squat when it comes to figuring out if a series is in fact convergent or not. So, all right, guys. I think that's it for this week for the video. When we get to class, I'm going to have some other news for you. So if you've watched this video ahead of time, then you're already going to know a little bit about it. The district is allowing us to have small groups of students on campus. And what I'd like to do is offer up the opportunity for up to 15 of you to come to class during our normal class time. So starting next week, I'll have some sign-up sheets, and I'm not exactly sure how we're going to do this because it's going to have to be on like a first come first serve for each day. And then if you came to class, for a live class on Monday, then I need to make sure that the other people who didn't get in on Monday have the option to sign up for Thursday. And then if there's extra space, we can have other people. And my room maxes out at 15 people for safety reasons, for COVID social distancing. So I probably will have a Google form that will figure out how to limit that for people who would like to come. And the idea would be that you would show up to school a little bit early. I'll have a video that shows how you're going to sign in, because you are going to have to sign in. But then you can come to class. You'll probably watch the video live. I'll be there in class. You'll probably want to have your computer with you. But then when we do the breakout rooms and stuff, you wouldn't obviously be in a breakout room with people in Zoom. You'd be in a breakout room in the room. Um, and it'll give us an opportunity to meet each other in some cases, and in other cases say hi to each other, and then just kind of get some live face-to-face interaction time during the homework time, and then we'll come back at the end and we'll be filming again at the end. So that's coming next week. So I'll have more information for you about it in class on Thursday. All right, guys, thanks for hanging out and watching the video, and I'll see you in class.